Hello. In a previous video we discussed the theorem here on the screen, and in this video I want to show you how this is applied. Alright, so what does the theorem say? Well, we have a vector function R, which is a three-dimensional vector function, so it has component functions x, y, and z, and it is defined on an open interval containing some real number a, but not necessarily at a itself. And we've got a vector c, c1, c2, c3, and r3. The theorem says that under these circumstances, the limit of r of t as t goes to a is c, if and only if the limit of x of t as t goes to a is c1, the limit of y of t as t goes to a is c2, and the limit of z of t as t goes to a is c3. Right, so this says when you're dealing with a limit of a vector function, you can work component-wise. In other words, you reduce the problem to a problem involving limits of r to r functions. And we know very well how to deal with these. So, what is the application? Well, here's an example. Let's say we have two vector functions, r and w, both defined on an open interval containing a, except possibly at a, and we have two vectors c in d and r3. Do we assume that the limit as t goes to a of r of t is c, and the limit of w of t as t goes to a is d? Then the limit of r of t plus w of t exists as t goes to a, and this limit is equal to c plus d. Right? So what we've got here is limit t goes to a r of t, right? That's c, plus limit t goes to a w of t, right? Which is d. So this is a sum rule for limits of vector functions. And we're going to prove this using our theorem 1, which we showed a moment ago. So, right, we have a theorem to prove. Right, so we must carefully identify what are the assumptions. Right, so our key assumptions are limit as t goes to a of r of t is c, and limit of w of t as t goes to a is d. These are our assumptions. Right? In other words, the things we can use. And what are the conclusions? In other words, what do we want to prove? Well, we actually want to prove two things. First, we want to prove that the limit of r of t plus w of t as t goes to a exists, and we want to prove that this limit equals to c plus d. So we have two things to prove. Now, what are the tools at our disposal? Well, we've obviously got theorem 1, right, which tells us we can work component-wise. But that's not going to be enough. We need something else. Right? We also have the sum rule for scalar functions, so for r to r functions. Right, and what does this result say? Well, it says if the limit of t going to a of a function f of t is L, the limit t goes to a of a function g of t is M, so f, g are functions from r to r, then the limit of the sum of these two functions, so f of t plus g of t, this limit exists, and it equals L plus M. So the sum of the limit of f and the sum of the limit of g. So these are the two things we have at our disposal. Right? The tools we can use. Right? So let's just look again. Our assumptions, the things that are given in the theorem to be true, and we have our tools. Right? These we can use to get from the assumption to the conclusions. Okay. So let's see how we're going to prove this. Right, so let's call that SR for sum rule? Well, so let's say R of t has components x, y, and z. W of t has components u, v, and w. Right, so then what does R plus w look like? Well, we're just adding vectors. So we're adding component-wise. X plus ut, y plus vt, zt plus wt. Right? So these are the components of our vector function R plus w. Okay. Now what do we know? Well, we know that the limit of R of t as t goes to a is c. So what does that tell us? Well, by theorem 1, right, we know the limit t goes to a, x of t is c1. We know the limit t goes to a, y of t is c2, and we know the limit t goes to a, z of t is c3. Right, and let's label this 1 so we can refer back to it later. Right. Now we also know that the limit of wt as t goes to a is d. So again, by theorem 1, right, we're using that theorem again, we can go to the components of w. So w has first component u of t, so that limit should be d1. W has second component v of t, so that limit should be d2. And the third component of w is little w, and that's going to be d3. Right. So let's call that 2. Right. Now we need to somehow get to the components of r plus w. So we need to get to these guys. Right. And this is where the sum rule for scalar functions come in. So for functions from r to r. Right. 1 and 2 tell us that these scalar functions, x, y, z, they have limits c1, c2, and c3 respectively. And 2 tells us that the scalar functions u, v, and w have limits d1, d2, and d3. So we can apply the sum rule for limits of r to r functions here. Right? So by the sum rule and these two, 1 and 2, we have the following. We have limit t goes to a, x of t plus u of t. Right? We're looking at the first component of w, of r plus w here. Right? This exists and is equal to c1 plus d1. We also know that the limit for the second component exists, right, y of t plus v of t, that exists, and it's going to be equal to d, right, let's rather say c2 plus d2, right, and the limit t goes to a of the third component, so that's z of t, w of t, that exists and is equal to c3 plus d3. Right. So what have we got? Well, we used theorem 1 to show that the limits of these scalar functions, x, y, z, u, v, w, all exist and equal c1, c2, c3, and so on. And then we went and applied the sum rule for scalar functions here, right, to see that the limits for the components of r plus w, right, they exist. Right, remember, x plus u, this is the component, or the first component for r plus w. Y plus v, that's the second component of r plus w. Z plus w, that's the third component. Right? So the sum rule and 1 and 2 here tell us that these limits exist and they're equal to c1 plus d1, c2 plus d2, and c3 plus d3 respectively. that means that we can apply Theorem 1. So by Theorem 1, the limit t goes to a, r of t plus w of t exists. Right, that's the first thing we wanted to prove. And what is the limit? Well, we have to look at the limit of the components. Right. So the limits of the components of r plus w, c1 plus d1, c2 plus d2, and c3 plus d3. So this vector goes to c1 plus d1, c2 plus d2, c3 plus d3. Right. And we know what that is. Right? We're just adding two vectors here. C1, C2, C3, D1, D2, and D3, and that's C plus D. And we're done. Right. So it's important to note here that we're proving two things. We're proving that the limit exists, and we're proving that its value is C plus D. Right. So before you can write this expression, limit t goes to a of r of t plus w of t, we must first know that the limit exists. Right. And Theorem 1 does give us that. Right. Now, you can of course go ahead and prove all sorts of limit laws for vector functions, and the proofs all follow the same principle. Right. You can look at Theorem 5.2.2 in the course notes.